Hello, welcome back to my channel, my friends. So in this video I am going to again do a tutorial on Proteus Simulation Software. In this tutorial I would quickly go through the method of importing third-party spice model in our Proteus Simulation Software. As you guys have seen in my previous videos, how to import third-party spice model in LT Spice software, in which I have gone through very detailed method of importing a third-party spice model in LT Spice. So now I'm going to here show you how to import the spice model in Proteus Simulation Software. You guys might have already gone through various online help in which most of the developers have shown how to import the spice model in Proteus. But just for your information, I want to tell you that these resources available online do not show the actual result of the transistor working. Like to say is that they show the simulation graph on the Proteus, and they show that the DC characteristic curve is working, is being simulated. But if you compare those graphs with the actual data sheet of the transistor, then it would never match. You can find and do a research by yourself if you see this graph. Like, so you can see here that this graph only shows the current in microampere. As you can see that this is 900 microampere only, and the maximum current that is flowing through the transistor is 1 milliampere, so which is not right. And therefore I have decided to do this video or tutorial to show you actually how to import the spice model and how to basically run the spice model in our circuit, which gives us the real results, not the simulator default results. So let us first decide what transistor we would select. So let's go to the DG key and I simply type here FET. So let's select MOSFET as our transistor. So now let's select this first transistor. This transistor available in a very high stock, and it is from Diodes Incorporated. So Diodes Incorporated mainly issues the spice model of their products. So we would simply copy this part number and go into the Diodes Incorporated website and search for this part number. This is the EDA model, not the spice model. I am going to show you how to download spice model. Now here, as you can see, that they have provided the spice model. Alright, so this is spice model. We can simply see here that most of the nets are available here, and the sub-circuit spice model is provided here from Diodes Incorporation. So what I would do here, simply delete this. This is not necessary to delete, by the way, but I will do this. And just to make things simple and clear, I simply going to save as this file into my folder which I have created for my project. Let's do this as dmn65d8l.lib. It is important to mention here that when you download the spice model in text file, then you should rename and save this file in the extension of .lib and select the save as type as all files, not txt, all files, and always save the file in the project folder which you have created for your project. Okay, now click save. Right, now we close this, and and now we go to our Proteus schematic. Now we would simply go here and choose the transistor. In transistor, in generic, we go N channel MOSFET. By the way, this is an N channel MOSFET, so we would select this N channel analog primitive N MOSFET. Just remember this in generic type. And now it's time to do the DC biasing. DC biasing, we put DC source for the gate, DC source for the drain, and we would simply ground the source terminal. As you people know that the DC characteristic curve is for the current probes, because it shows the relationship of the drain current to the drain to source voltage at applied particular gate to source voltages. So N MOSFET always work on the positive gate to source voltage. So I will simply leave this as it is and rename this as VDS, and I would rename this as VDS and rename this as IDS. Okay, and now I would go here and do the transfer characteristic curve analysis of this transistor. I would simply go here and drag this probe into my DC transfer characteristic curve analysis and double click on this graph. Now on the left hand side you see that there are two voltage sources. Select the VDS. On the right hand side select VGS. Alright, now let's see the data sheet of this transistor which we have selected here. What this data sheet says. Most of the time these transistors have data sheets given transfer characteristic curve. So what I would do here is to match the data sheet transfer characteristic curve with my Proteus simulation transfer curve which I will get here, in order to verify that the simulation model, SPICE model, is obviously working as expected. While others resources which you go in different websites, you see they don't really verify their SPICE model working. So scroll down and see the transfer characteristic curve here. As you can see here, this is the curve. So what we see here is that they swapped the drain to source voltage from 0 volt to 5 volt, and they swapped the gate to source voltage from 2.5 volt to 10 volt. So I would simply swap the drain to source voltage from 0 volt to 5 volt like they have done with 100 steps, and gate to source voltage from 0 volt to 10 volt in 10 steps. Okay, this is very simple. Press OK. So now it is time to integrate our SPICE model to this schematic symbol. When we double click the SPICE, the schematic symbol of the transistor NMOS, we get something like this. And what we would do here is that we write here sub-circuit, and we write here SPICE file equals this name which we have given the name of the SPICE model here, You simply copy here and paste here. .lib, and I would have also like spice model equals this. This spice model file contains this spice model dmn65d8l. This is the file name with extension .lib, and in this file the model name is dmn65d8l. Okay, so what this would do is that this transistor NMOS would extract the spice model from my given file location and do the simulation in our schematic. So let's see what it gives us. Boom. Here, as you can see, our model is working perfectly fine. Let's see what this graph tells us. Now click on this green bar, double click, not on the black side. Click on this green tab and you will get the full window view. Now let's compare our result with the data sheet. As you can see that at gate to source voltage 2.5 volt and around 3.5 volt VDS, we are getting the drain current to be around 200 milliampere. Okay, so we should be getting like this in our simulation. So as you can see here on the bottom right, this is 3 volt, and this has not shown, the simulator has not taken the 2.5 volt because I have taken only 10 steps. So I would go with the 3 volt here. So let's take 3 volt. At VGS 3 volt and drain to source voltage to be at 3.5 volt, the drain current is around like 500 milliampere, less than 500 milliampere, 480 milliampere around. So let's see, at VGS 3 volt and VDS to be at 3.5 volt, I think it was 3.5, yes, 3.5 VDS and 3 volt VGS, 3.5 volt VDS. As you can see on the bottom left, 3.5 volt VDS, and on the bottom right it says that VGS is 3 volt. So you can see here the drain current is 420 milliampere, which is quite near to the data sheet. 420 milliampere lies something here, would lie here, but it is showing more than 450 milliampere. But for the sake of simplicity, I would take this as approximate, and it is close to what we were expected. So now let's see what we get at VGS equals to 4 volt. As you can see, this curve here is 4 volt curve, and at around 1.5 volt VDS, this curve has around more than 500 milliampere current flowing through the drain terminal at 1.5 volt VDS, and VGS equal to 4 volt. So let's select VGS equal to 4 volt, where here is VGS equals to 4 volt, and VDS to be at I drag this cursor down to 1.5 volt, and I see here that VDS is 1.5 volt and VGS is 4 volt, and our current is 500 milliampere, which seems to be okay to me, because if you see very closely, this is the curve, and this is the point here. Here is the point, and this is around maybe 510 milliampere, 510 milliampere, and we are getting 501 milliampere. So in my opinion, it is okay. So this is how it works. Most of the resources shown here to import the spice model in Proteus are not accurate, are not okay, are not correct. This is the correct method to import the spice model in Proteus for a transistor or for any other integrated circuit which you want, like op-amp or amplifier or BJT. So this is it, guys. And also we can increase our sweep value, like say we want to sweep this to 50 volt VDS 50 volt, and we can increase our number of points, number of steps to like 200 would be a bit less, like 1000, and we resimulate, and we can see here, this is the graph you might be looking for. See, this is a particular typical graph of a transistor characteristic curve which you might be interested in to see. This is not here, on the left scale you can see no microampere current flowing. This is a real practical simulation of the transistor characteristic. So this is it, guys. I hope you liked my video, and please do subscribe to my channel. Thank you.